In this video, we'll be covering the concept of Newton's method. Newton's method is a way that we're going to use derivatives to approximate the root or zero of a function. So what's going to happen in the concept is that if I've got myself a function of some sort or another that I know clearly crosses the x-axis somewhere, I'm going to go ahead and identify any random point on the function. That point we're going to go ahead and call x1. If I can go ahead and identify the tangent line at x1, that tangent line again will look something like this. Notice that tangent line will cross the x-axis somewhere else, not necessarily at that point. However, you'll notice if this is my x1 value, right about here, my x2 value, which is what we're going to call that point, my x2 value will actually be closer to the actual root. So if I go ahead and identify this, I find my tangent line at that point, I get an x2 value, I trace my x2 value back up to the graph, and there I create myself another tangent line approximating curve. So there is another tangent line. You'll notice I now have an x3 value that's a little bit closer to my actual root. So we're going to continue this pattern all the way through until we get the best approximation of this point that we can. Now, the way that we're actually going to do this mathematically, again, this is the concept, but mathematically, remember these are just tangent lines, and tangent lines are of the form y minus y1 equals to m times x minus x1. So now this x1 actually matches up perfectly with this x1 here. Now again, it's going to change every time we do it to x2 and x3 and so on and so forth. But what I need to do is I need to find a formula that will allow me to find this x value. Okay? So, with that concept, what I'm actually going to have here is, well, let me rechange or identify all of these pieces. Remember, m is nothing more than the slope of this tangent line. The slope of this tangent line is nothing more than f prime of x1. Okay, again, one more time, that's the x1 value. The derivative at that value gives me the slope. If I plug in x1, it gives me the slope of that tangent line perfectly. y1, on the other hand, that value is nothing more than just f of x1. Okay, so rechanging or re-identifying all these values here appropriately, I get this tangent line. Again, this is the derivative at x1, and this is the function value at x1. Then this is x1 itself. Now, the idea is we want y here to be 0. Again, we want to know what does this line do if my y value is guaranteed to be 0. If it's guaranteed to be 0, that gives me my x-intercept of that tangent line. So let's assume for a second that that is 0. I now have this equation. With that equation, what we're going to identify is that, well, I can solve for this x value. Again, anytime that I'm solving an equation for x, I'm getting myself an x-intercept if I've set that function, that y value, equal to 0. So in that case, I have negative f of x1 equals to f prime of x1 times x minus 1. I will then divide everything by that slope value. Again, divide everything by that slope value. This provides me with x minus x1, and again, I'm switching the order of which these things look, equals to a negative f of x1 divided by f prime of x1. Lastly, if I add the x1 to both sides, I get my x value that I'm looking for is x1 minus f of x1 divided by f prime of x1. So this right here is the formula that we're going to use to identify what x2 is supposed to be. So if I re-identify this x as x2, I now have a formula to find x2. If I want to find x3, x3 will be nothing more than the same formula, except for I am now using x2 for all of my x values. Again, one more time, this is the concept and the formula. Anytime I want to try to approximate a root on a function using the tangent line. And again, notice I can change this for every single term I'm looking for, and it's the exact same formula.